Good afternoon, everybody. It's Sunday afternoon at PyData London, so I think by this point it's only the most dedicated Python data nerds left in the room, so thank you for being here. I would like to talk to you about transformer internals. Now, those of you who went to Sam Joseph's talk, or tutorial rather, on Friday, you might think, well, actually, I know all of this stuff, and actually, yeah, to an extent you do, and his presentation was definitely better than mine is going to be. Nevertheless, what I'm going to cover is more about the internals of the transformers library built by HuggingFace. And then I'll have a little bit to say about some of the things Sam mentioned previously at the end. So everybody and their dog is using transformers, but how well do we really understand how it works? I want to take you through very briefly an explanation of how transformers work, just for background. Now, I emphasize very briefly because I think, based on my experience of PyData so far, it will probably be the fourth or the fifth explanation of how transformers work that you've seen this weekend. You maybe don't want too much detail there. Besides which, a detailed explanation of how they work is a different talk, so I don't intend to go into too much depth there. What I want to do then is give you a tour of HuggingFace transformers, of the library, of the internals, and give you at least a taste of how it's implemented under the hood. Why would you want to do that? Why would you care? Well, a few reasons I can think of. Firstly, that personally I'm a big advocate of learning from code. So we can become better engineers and we can learn about how to structure large libraries and manage large projects by reading code by people who have done that before. And the HuggingFace Transformers library is an enormous open source effort by a very large number of people. There are elements of it that are really good, really well designed, and we can learn a lot from it. There's also elements of it that some people might critique or think, oh, I could do that a different way or a better way. That's okay too. Actually, there's a huge number of complicated trade-offs that come when we build things like this that lead to the engineering decisions that the maintainers of these libraries make. And we can learn from that too. So learning from reading code, and personally, I've enjoyed the journey of learning the insides of HuggingFace transformers, at least to a degree, in preparation for this talk. And that is to say, as a caveat, that I'm actually not an expert, and I'm certainly not a contributor to HuggingFace transformers, but maybe from this talk, I'll spark some inspiration in one or two of you, and you'll become contributors, and that would be fantastic, because open source always needs more people and more minds to contribute to it. And thirdly, it's just fun, let's be honest. That's why we're all here on a Sunday afternoon at PyData in London, right? Because it's fun. So, a little bit about me. My name is Matt. I'm the CTO and one of the co-founders of a company called Fuzzy Labs. So we are an AI consultancy based up in Manchester in the UK, and we specialize in helping people productionize AI. So we cover the entire life cycle from data, model, production, monitoring, everything in between. We love open source. We use open source in pretty much everything we do as well. And for me personally, I'm interested in, well, probably everything, but if I have to narrow it down, AI, machine learning, of course, functional programming. I like to write Python as low as Haskell. My team loves that. And bio-inspired computing is good fun. All right, so I want to ask a quick poll to the audience then. Firstly, how many of you feel like you understand how transformers work? And bear in mind, like I say, there's been about 4 explanations of this so far at PyData, so show of hands. Okay, that's interesting, because actually it's fewer than I thought, so maybe actually the explanation I'm going to give, hopefully that's the one that creates the intuition. We can only hope. How many feel comfortable using HuggingFace, just day-to-day consuming the library? So that's good. What about how many feel like they really understand how it works internally? So this is the bit where I was hoping one person would put their hand up and the joke would be, okay, come up and do the talk. But never mind, I suppose I'll have to do it. Right, so firstly, how transformers work in theory. Let me try to cover this off. So firstly, a bit of a definition. Transformers are a model architecture for dealing with sequential data. And often when we hear sequential data, we think about text, but it doesn't have to be text. It could be audio, it could be images, it could be video, anything that we can put into a sequence. Its notable features are that it's highly parallelizable at training time. So we're able to work on enormous amounts of data, and that's part of what led to the large language model revolution. The second feature is this self-attention. Self-attention is this idea that we can capture the relationships between elements in our sequence. I'll say a little bit more about that in a second, but the key thing is that the transformer architecture relies solely on attention to do what it does. Hence the name of the paper that you've probably all heard of, Attention is All You Need. It's because attention is all you need. That's the claim made by the paper. That's why it's named that. Now, it's quite an accessible paper, incidentally. If you've not read it, give it a go. So we'll go through 3 slides just to kind of explain how we build this up. So suppose we want to generate some text with transformers. We're going to come back to the canine theme because I like dogs. So once there was a dog named what? And you might think of a bunch of different dog names. And if we were to order in terms of like the most frequent to the least frequent dog name that we might encounter across all English language text that we can find, then we would get a list maybe like this. I don't know if Rex is the most common dog name. I put it there simply because when I ran this, Rex came out, so I've just picked Rex. So don't take this as a representative example, it's just an illustration. But you can imagine then, you iterate on this, right? So you say, okay, there was a dog named Rex, now what? What's next, what's next, what's next? So all the transformer model is doing is generating the next token. Now, I've made a subtle distinction here as well, because I've said large language models use transformers to generate text. Transformers can do all kinds of things. They can do translation. They can do like sentiment analysis and recognition of elements in text. And they can do this predict the next token task. That's one of the remarkable things about transformers. It's that for the whole universe of different natural language processing tasks that you can think of and that the field of NLP has looked at for the last few decades, can all, it turns out, be covered by this same model architecture. So while usually when we're talking about this stuff, we're talking about large language models and we're talking about predict next token, I just want to point out that that is one task of many that can be implemented in a transformer. For today, I'm going to focus on large language models. I'm going to focus on predict next token, but that's not all there is to it. Okay, so here's the explanation that you're probably sick of. Okay, so firstly, we have to break that sentence down into tokens. Tokens are kind of like words, but it's more accurate to say they are the most fundamental part of the sequence that we can divide that sequence into, if that makes sense. I've not picked a great example here, right? Because actually, our tokens are all words, with the exception here where we say you could divide named into name and a final D, right? Because that makes it a past tense verb rather than a noun. So those are distinguished as tokens. But you can imagine with bigger words, you know, like transformer is transform and as an ending, which you find in other words, and so on, right? So that's the idea of tokenization. Next, what we want to do is take each of our tokens and assign them a vector. And the reason we do that is because we want to imbue the transformer with a notion of meaning. So what do these tokens actually mean to us? So the idea is that we construct a vector space with the property that tokens that mean similar things are geometrically close to one another. And it's really that simple. That's the intuition you need. So in this example, dog and cat ought to be nearby. Xylophone ought to be very, very distant. And when we talk about distance, we're almost always talking about cosine distance. So it's the angular distance between the two vectors. Also, this is a two-dimensional example. Of course, our vector spaces are many, many, many more dimensions than 2. But never mind that. I'm just building intuition here. And then final little caveat here, important to add. We're not just encoding the meaning, we're encoding the position. Where in the sequence does this token appear? And you know, I'm going to refer to Sam Joseph a couple of times because his presentation was fantastic. Sam had a great example, which was his knock-knock joke. The word knock, it has a different sense of meaning to the second knock in knock-knock. It tells you this is about to be a joke, right? So that's the idea. Well, what do I know? I'm not a comedian, mind you. So that's how that works. Incidentally, you may laugh, but it won't be at my jokes. It'll just be at me. So finally, we get to self-attention, right? So here what we want to do is think about each vector in terms of the context in which it appears. So what do the other words add to this word that tells us more about what it means in context. This is the magic that makes transformers work as well as they do. And I'm not going to try to explain the self-attention mechanism in any more detail than this, because there are far, far better resources out there for you to learn from, and I'd refer you to them. But the idea here is let's compare two sentences. So the dog didn't cross the road because it was tired. The dog didn't cross the road because it was too wide. We understand that it, in these sentences, has a different meaning. It refers to something else earlier on in the sentence. And I'd ask you to imagine that you are in fact the word it. Now I realize that's quite an abstract thing that I'm asking you to imagine on a Sunday afternoon. Nevertheless, imagine you are that word it. And you ask yourself a question. You ask yourself, of the words that came before me, which of those words am I most strongly attached to? Which of those words do I bind to most strongly? That's what self-attention is doing. It's learning how to make those relationships. And there are diagrams like this that you may have seen where we can map out for every pairing of words that we see in our sequence an amount of attention that they pay to one another. I didn't generate this, but it comes from a wonderful blog which is linked below, which I highly recommend. Okay, so far, so good. We've understood transformers, well, maybe. If not, I apologize for that, but have a look on the internet. Let's have a look at HuggingFace. So I've got a bit of a problem, actually, a bit of a semantic issue with HuggingFace. I love HuggingFace as a library. I'm a big fan of it, just to be clear. And I know this will be on video as well, so I really have to be clear about that. However, my problem with HuggingFace is that they are kind of name squatting, right? Because as we've just seen, transformer is a type of model architecture. It's an abstract concept. There can be many implementations of transformers. However, HuggingFace got there first and named their library transformers. So now we kind of conflate the two. And we say transformers and we think HuggingFace. It's a little bit unfair. Well, how did it come to be that way then? Well, aside from HuggingFace, the company, being named after the most fun, most important Unicode code point, everybody's favorite, it actually started out life a little bit differently. So originally it was PyTorch pre-trained BERT. And what they did was they did a PyTorch port of the BERT model. So Google came out with the BERT model that was trained using TensorFlow, which is Google's library. And the HuggingFace team said, okay, well, we're going to port this over to PyTorch. And they released this. And if you look back on the GitHub repo, all the way back, you will see a README that reads, this is an op-for-op PyTorch reimplementation of Google's TensorFlow repository for the BERT model. That's where it started. Of course, naturally, that kind of worked quite well. They got reasonably popular, got some traction, they added more models to it. So it's no longer BERT, it's now PyTorch Transformers. But then the next iteration, we actually want to support more than just PyTorch. So we support TensorFlow and JAX as well. So now it's just Transformers, and that's how we got to the world we live in today. And then finally, just to disambiguate, you also have the HuggingFace hub, i.e. the website that we go to download our models from. So these things are very closely intertwined, as we'll see when we have a look at the code. So let's do that. I am right now SSH'd into my desktop at home, which has a GPU. And if the connection breaks, then things are going to go wrong. But we'll try, right? This is hello world in 9 easy lines. That actually is a joke. You don't have to laugh. But the point is, right, this is kind of a ridiculous hello world for me. It's a little bit too long, but nevertheless, we'll work with it. So what is this doing? Well, firstly, if I run this, we'll find, for example, once there was a dog named Rex. He was a very good dog. I've not met Rex, but I am inclined to believe that that's true. So actually, what we can do is run it. I should actually have set up this bit beforehand, but never mind. Yeah. Apologies. Let's do that. Good, right. So we can actually copy paste this piece of code right in here. Yes, I do still use Emacs. And I will never stop. We can run this, and we'll load up a model, and just to prove that it actually does something, and then we'll look at how it does it. Once there was a dog named Rex, he was a very good dog. Great. So my temperature must have been quite low, right? Because I've actually managed to generate exactly the same thing again. But that's nice. All right. How did this come about? Well, the first line is actually really easy. It's just the name of our model. What does that correspond to? Well, we can jump out of our slides for a moment and have a look. So every model name has a corresponding page associated with it on the HuggingFace website. I realize probably most of you already know this, but I want to make sure that we're starting from the same place on this. And moreover, so this is the model card that you'll see, kind of description of the model and all this sort of thing. Moreover, if you look at the files, you will find there is a bunch of files associated with the model. This is what gets downloaded in the background by the transformers library when you load that model. A few things of interest here. We've got a config file. We'll come back to that in a little while. But I said that Mistral is one particular implementation of the transformers architecture. We need to configure how we want Mistral to be a transformer, if that kind of makes sense. So we specify what architecture we want to use. We specify a bunch of other things, hidden layers, all these sorts of things. And that represents how we want to configure this model when we load it. And then you have the model binaries themselves. So these are the weights. Safe tensors. How many people know what safe tensors is? So that's really interesting and allows me to move on to my next tab. So safe tensors is very important, and we should all know what it is, because it turns out that saving models in things like pickle files is really, really dangerous, because you can hide executable code in pickle files. And you can have it such that when you load this model in production, some malicious code runs and does something that you don't want it to do. Safe tensors is a model format that HuggingFace has put together that's intended to prevent that, hence safe, right? So the idea of safe tensors, and I think it's now just a standard across a great deal of the models you'll find, if not all, but don't quote me on that. But it particularly avoids executable code inside your model file. So that's pretty important. The good news is that you get it by default here, right? So you don't need to worry about it, but you should be aware of it as anybody who's intending to deploy these models to production at least. All right, so we've looked at the model file. Maybe we need to have a look at this, and I won't full screen this slide. You can see what's here. You can see my speaker notes as well. Why not? Good news, everyone. We're going to have a look at the code. That was my point. I've tried to get a few memes in here. So where are we going to go? This is where I need my notes. So actually, let's have a look at the Git repo for, don't do that, Git repo for transformers first. So as we navigate this, we're first struck by the fact that it's probably too small to read, but once we make it a little bit bigger, we're struck by how much code there is in here. And I am looking for source transformers. And we look in here, we look at models. And the next thing we notice is there's a surprising number of directories in here. When I first looked at this, I was really quite surprised because I didn't really understand how this worked, but I kind of assumed that either there was like a generic notion of a transformer that you configure in different ways, or that the specific models come with their own implementations. It turns out that all of the model implementations live inside this directory. And it's huge, it's enormous. And we're going to come across that theme a few times in this talk as well. What the line of code that we were interested in, if I just remind you, was this auto tokenizer from pre-trained. So we'd like to understand how that works. So we'll go to this, turns out we go to the auto directory, and in there we will find tokenization auto. Then we switch back to Emacs and we're all happy. So let's have a look at tokenization auto. What does that do? Lots of things, it turns out. So to begin with, put that down there. Right, so we were calling from pre-trained, right? I will make this bigger in just a second. We just need to do, this is quite hard to do while looking that way, so apologies. But let's make that a little bit bigger. We're not going to read this line by line, by the way. We'll be here all day, I promise you. But let's just kind of get a feel for this, right? So from pre-trained, let's have a look at the doc string. It says it's going to figure out how to instantiate a tokenizer class based on the model type, based on the name or the path that we give it. So it turns out then that we need different tokenizers for different models, and there's an affinity between the tokenizer and the model. That's good to know. I'll kind of scroll through this. I will then ask you to take my word for the fact that ultimately, once it's decided, I think maybe we can find it, so we've got this tokenizer mapping names. Ultimately, it's going to need to look up where this tokenizer comes from. And that's where we can say, goodness me, tokenizer mapping names. Right, this is what we want to look at. Tokenizer mapping names, right. And we get a kind of similar feeling to what we got when we looked at that big directory. A huge, massive list of things here. So every single model has to be defined in here, and we have to say what it maps to. So Mistral is here, and now here's our next little surprise, or maybe not a surprise to everyone, but turns out the Mistral doesn't have its own tokenizer, it's the Llama tokenizer. Okay, so actually it turns out Mistral is built on top of the Llama model architecture. Yes, it's its own weights, and it's been trained independently, and it does its own things, it's got its own twists, but fundamentally, it's actually based on the Llama architecture. So that's going to be a common theme that we'll see. Rather than looking at the Mistral tokenizer, or rather the Llama tokenizer, we can actually run it. So let's do that. I ran all of this code earlier, which means I now have a thing in my environment, and this is why I'm doing it in a Python terminal instead of just running a script. I have a thing in my environment that's called a tokenizer. I can run that and find out what it looks like. It's a Llama fast tokenizer, or Llama tokenizer fast. I'm glad it's fast, but that's the concrete implementation. So auto tokenizer has gone and found this and given it back to us. And we can query it. So we can say, okay, well, PyData has the best food, which is true. And it's going to come back with some tokens, but, you know, that's not particularly readable, so maybe we just call tokenize on top of that there. It's going to be great fun to watch back on the video with me fumbling around with my keyboards looking the wrong way. And we get this, right? So that now we can kind of see actually what's it going to break down to, what tokens is it going to give us back. Cool. The first thing is like these, you know, this is actually what we need in order to run the model, but this is what we need to just understand what's happening there. And you know, maybe we can try one other thing. What's a long word that might break, hopefully. Is that spelt right? Yeah? There we go, cool. So we can break this word down into its component tokens. A very, very common word, I use it every day. Right, fine. So we've looked at the tokenizer. Let's move on to something a little bit more interesting than tokenization, which would be, just hide that out of the way so you can see a bigger version of it. This. So a little bit of deja vu here because previously we had auto tokenizer, now we have AutoModel. And I'll just full screen that just for the fun. We know what this is from, right? The Matrix? If not, go watch that. Anyway, there's more auto magic going on here. So, all right, let's have a look at that. First thing we can do is take a look at the documentation. It's always a good place to go. Make that a little bit bigger for you too. Maybe even bigger. All right, cool. So what does it say here? In many cases, the architecture you want to use can be guessed from the name or the path. So what this is going to do is figure out what model you need to load. Just like before we had auto tokenizer, it figures out what tokenizer you want to load. Now we want to figure out what model we're going to load. Okay, that's good. It also mentions something about tasks in here. I can just find it. What's the word task? There we go. So there's one class of AutoModel for each task and one class for each backend. Well, backends are easy, right? Because we support PyTorch, we support TensorFlow and JAX. What do they mean by task? They mean the kind of operation you want to perform. What you'll notice if we just jump back to this code is that actually we said AutoModel for causal LM. What is that? Well, it's causal language model. So what that refers to is the task of predicting the next token. There's a bunch of other tasks that you can perform with transformers, and you have a different class for each of those. So we're saying not just that we want an auto model, we want one that does this task specifically. And on PyTorch, PyTorch, it turns out, is the default. Fair enough. So I'm going to go back to Emacs where I feel warm and comfortable. And we're going to jump over to this thing called Modeling Auto. So what does Modeling Auto do? Well, a whole bunch of things. The first thing I want to show you is just the class AutoModel. So AutoModel 4, any guesses how many of these we have? We have quite a lot, actually. So if I actually list them out, 1 second. There. No. There we go, one I did earlier. So that's every single class that starts with AutoModel 4. Now, okay, fine, there's duplicates in here, but kind of just to give you an idea, right? We've got, token classification, we've got question answering, we've got image classification, so on and so on. So a large number of different tasks that we could do if we wanted to. In any case, we need to know now how it actually finds the model. So we can look for this other, and again, you'll take my word for it because I'm not going to go through how it builds this up because it's complicated and will take too long and probably a bit boring too. But what I can do is show, oh goodness me, model for causal, this is a good constant name list, causal LM mapping, right. So it's this thing, model for causal LM mapping. We have yet another massive dictionary. And what this does is tells us where to find all of the concrete implementations of the models for our causal LM class, task rather. So we look for Mistral and we find our Mistral for causal LM. Okay, fair enough. So we're going to keep digging a little bit more. So we're now going to go to, it turns out, this file called modular Mistral. And I'll just show you where that lives in file space. So where I am here, I just go up one level. This is the same models directory that I just showed you in the GitHub screen. So this is every single one, and then we go to Mistral, and we jump into here, and these are all the files that we get, and typically each model looks more or less the same. The auto directory is a special case because it's not really a model, but it acts like a model because it's supposed to find the right model for you. So that's kind of cool. Modular Mistral is the thing we're after, and we notice something that is simultaneously a surprise and not a surprise, because actually Mistral for causal LM is pretty much empty, and it inherits Llama for causal LM. Okay, so actually we're in Llama land again. So we'll go there. We won't actually bother to look at the Mistral implementation, but something I do want to draw your attention to is the config. So we saw that earlier. There's configuration Mistral here. So when we actually load the model, when we instantiate the model ultimately, and actually just before I do that, I will show you one other thing, which is we will go to modeling Llama and just have a look at what that looks like, just to complete the chain there. So this is the class which is inherited by modeling Mistral. So this is the thing. This is actually the model now. And within here, you find all kinds of exciting things that you can read in your own time, like how they implement rotary embedding, how they're applying rotary embedding, all this sort of thing. And what else? Key value lookups, the attention mechanism, the forward function, so actually the forward execution of the model, and so on and so on. Go through that in your own time, something to do this evening, I'm sure. In any case, let's have a look at the config because that's a little bit more digestible. So Mistral config, it says it supports a whole bunch of things. Things that are not too surprising, things you've probably seen if you've instantiated these models using HuggingFace. For instance, how big is the hidden layer? How many attention heads do we want? How many key value heads do we want? And so on. All this stuff is configurable if you want it to be. And that's how Mistral sort of instantiates itself. Fair enough. Then the last thing I wanted to look at, just because if I go on too long, you probably will get bored of looking at my Emacs screen, is generating. So let's come back to our slides. So we've kind of seen how tokenization works roughly. We've kind of seen how the model is loaded, and we found out that actually underneath Mistral is a llama. That's interesting to know. So let's come back to the original code. What about generate? What's going on there? Well, and once again, I want to give you minimum viable knowledge. I don't want to step through the entire generate function myself right now. But we can have a very quick scan of what it looks like. Anyway, there's this thing called and actually I think we'll see it if we look at the llama class again. And what I want is modeling llama and the causal LM class. Llama for causal LM, and we'll notice it inherits llama pre-trained model, but it also inherits this thing called a generation mixin. I haven't quite wrapped my head around this, if I'm honest, but the idea is that we're kind of bringing in some functions which can be shared across a whole bunch of different model implementations. So that is actually where our generate function lives, turns out. So generation utils contains a wonderful, enormous function inside that class. And where are we going? Generation config. So generation config actually is worth a quick scan as well, because this is the kind of thing that a lot of people will have seen and been familiar with if you're just using the library on a day-to-day basis. This is where we specify, for instance, what our strategy is going to be when we generate the tokens. How do we want to do that? How many tokens do we want to generate? What's our temperature going to be? All of that sort of thing is going to end up in here. And it actually, in the code we had one little parameter here, max new tokens, but you can put all kinds of things and you can specify that you want, different kinds of search strategies, for instance. All of those search strategies are implemented around here as well. There's a file here for beam search, for instance, which we won't look at, we don't have time, but that's the kind of thing we've got. And yeah, look, they're definitely not gonna read through, let's see how many lines of code, 16, 12 lines of code. But again, maybe this evening with a glass of wine, you can go through that yourselves. So I've got about 3 minutes left. So the last thing I just want to mention is kind of allude to the fact that this is actually pretty complicated. Well, of course it is, because it's a real-world library that supports an enormous number of use cases, has an enormous number of contributors and users, and its production scale. We can learn a lot from it, but also maybe we want something a little bit easier to start off with. I've sort of given the game away on this a little bit, but could we have a toy transformer model just to play with and learn from and experiment with that tells us the basic concepts, and then look at this to understand how those concepts are implemented at a bigger scale? Well, yes, we can, because Andrej Karpathy, the extraordinary genius that Andrej Karpathy is, has put together NanoGPT. And Sam Joseph, if you went to his tutorial on Friday, you will have gone through this yourself. But basically, in the repo, it takes you through preparing a data set, training a transformer model, and then running inference on that transformer. The code is accessible. You can read all of it. And by the end of it, probably have a pretty good intuition as to how this all works. So, finally, I'll just say thank you for listening. Thank you for at least not laughing at me, even though maybe my jokes didn't quite go down. And yeah, you can learn more about Fuzzy Labs here. I also have a newsletter on MLOps, which is semi-regular. And I'd like to just say thank you to the team at Fuzzy Labs as well, in particular, special mention to Danny Wood, who through various conversations and presentations at Fuzzy Labs has helped bring this together. And that's it. Thank you.